All right, good morning. We again forgot to make the announcement that things start a little earlier. Things look a little lighter. Is everyone aware of the Harry Gray rule that it doesn't matter how long you party, it doesn't count if you don't make it to the first talk? That applies. I see some missing spots of people that I always know sit in the same seat. We'll see. Okay, we are now on our last day of methods talks, and it is my distinct pleasure to introduce the first speaker, Frank Neese. Frank is without a doubt the person who has, to these workshops over the years, contributed the most talks. I think in 2012 he talked 4 times. In 2014, 2 times? 3 times. And now he's giving one methods talk on MCD, which was given previously by Nikolai, so we get a different viewpoint on MCD. And tomorrow he's giving a research talk and kicking off the student talk section. All right, without any further ado, Frank, we are glad you're here. Thank you.
So, thank you very much, Carsten, and good morning, everybody. I hope everybody's wide awake. At least I see many awake and curious faces, which is brave on the 6th day of such a workshop. And as Serena always says, like, if you're a man in the evening, you better be a man in the morning. And I hope that you all are ready for another treat. So the subject this morning is magnetic circular dichroism spectroscopy. And I wanted to ask, first, who of you has ever taken an MCD spectrum? Okay. Who of you have been reading MCD papers? Many. And who of you thought that this is the most confusing thing ever? Good. That's what I expected. And so let's see what we can do for you. And so the first thing when you do science is, of course, to be curious. And that has been realized since the ancient times. And of course there are many forms of curiosity. And you might be curious when you will finally get out of your PhD, or you might be curious whether the Lakers will win tonight, or you're curious when this guy will ever stop talking. But that's not the type of curiosity that I mean. The type of curiosity that I mean is scientific curiosity. And so today's subject starts with a guy who was extremely curious lifelong, and that was Michael Faraday. And Michael Faraday made crazy experiments that were way ahead of its time, and he documented them in his diary. And here's an excerpt from his diary from 1845, where he said, "Today worked with lines of magnetic force, passing them across different bodies, transparent in different directions, at the same time passing a polarized ray of light through them." I showed to you the thing in a second. And then he followed up, blah, 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 blah. But when the contrary magnetic poles were on the same side, there was an effect produced on the polarized ray, and thus magnetic force and light were proved to have a relation to each other. That is the type of thing that I mean. So that is scientific curiosity. He had absolutely no idea what to expect. He just did something, he observed something, and then he got curious why he observed what he did. So essentially the experiment that he did was the following. So he started with a polarized light beam. He passed it through some transparent matter, and he recorded the angle of rotation of the polarized light beam that was observed after passing through the sample. And he observed that this angle of rotation is proportional to the thickness of the sample, d, the strength of the magnetic field, B, so that's linearly proportional. And then there is a constant, a material constant that he called V, which is called the Verde constant, and that is a molecular property. So that's a property of the material that the light passes through. Here, by the way, is the magnet that he used at the time it's displayed at the Faraday Museum in London. So now this is our observation, and now we will gradually start to explain it and make use of it. So today, that is not really the experiment what we're doing, because what Faraday observed was what's called the optical rotary dispersion, ORD. And you can record that, of course, also as a function of the wavelength of the light. Now, if you have a substance that absorbs, like say in the visible region, and you scan the wavelengths of a sample, you get an ORD curve where on the y-axis you plot the angle of rotation, and on the x-axis you plot the wavelength. And so that is the so-called ORD spectrum. The ORD spectrum is rarely measured these days, but what is instead measured is the circular dichroism spectrum. And the circular dichroism spectrum is the differential absorption of right and left circularly polarized light as a function of wavelength. So if you have the three possible experiments here, then you have the absorption spectrum here, which displays some peaks. You have the circular dichroism spectrum here, where positive and negative peaks mean that like either the left circularly polarized light is absorbed preferentially or the right circularly polarized light is absorbed preferentially. Now the ORD and the CD, they have a mathematical relationship with each other that's expressed by a so-called Kramer's chronic transform. That's math stuff. It doesn't need to concern you at all. It simply means like if you have one, you have the other. Of the two, the circular dichroism is the one that's more convenient to measure, and hence when an experiment is done these days, it's still all Faraday, then it's a circular dichroism. Okay, so that is the observation, and now we need to start to explain it. So now we take a big step back. Never mind. That wasn't supposed to be there. Then it is. And so we'll talk a bit about photons, electrons, states, spectra, and all that. And you'll see a few slides that, like Serena already showed you. So I stole the slides from Serena, and Serena told you that she stole the slides from me. And you see, that's what love is. And so we steal from each other and like it. Okay, so first I'll look at the anatomy of a light wave. And so as we all know, light has wave character, and so there is a wavelength lambda. There also is a frequency that is inversely proportional to lambda. And associated with the light wave, there is an electric vector E, and orthogonal to it, there is a magnetic vector B. Then this is the propagation direction of the light wave, and the E and the B field is orthogonal to the propagation direction of the light. Now, parallel to the propagation direction, there is a wave vector K, and the absolute value of K is again inversely proportional to the wavelength and hence directly proportional to the frequency. Light also has a momentum. That is something that we use very little, but the physicists use a lot, and that momentum is directly proportional to the wave vector. And most important for today's lecture is that light carries angular momentum, and it carries angular momentum of a full unit of quantum mechanical angular momentum, like plus minus h bar. Now, a linearly polarized light beam is in a so-called superposition state between a right and left circularly polarized light vector. And so the right and left circularly polarized light is in a pure angular momentum state. So the linearly polarized light doesn't carry angular momentum by itself, but the components K plus and K minus, they carry one unit of angular momentum h bar. Good. Now let's get oriented a bit. When we do spectroscopy, I find it like really important that you visualize to yourself where are we standing in terms of energy and what relationship does that have to molecular phenomena. So let's look at the energy scale of optical spectroscopy, and the energy scale of spectroscopy in general. And let's start with like really high energy radiation, which would be gamma radiation at like 14,000 electron volts, and it goes all the way down to radio waves at like 10 to the minus 7 electron volts. So there are about like 11 orders of magnitude, like 12 orders of magnitude of photon energy that like a molecule can absorb and work with. Right? And so there are very different phenomena that correspond to these. And it's important that you like inhale this, and like that is a slide that should be in like the back of your mind whenever you talk about spectroscopy. Yeah, so for the very high energy radiation like gamma rays, you have nuclear processes, and Mössbauer spectroscopy is like the one in bioinorganic chemistry that certainly matters the most, where you have nuclear transitions, so like internal states of the nucleus. And then if you go a bit higher up in energy at like about 2,000 to like 8,000, 9,000 electron volts for the first transition row, you have all of the phenomena of X-ray absorption spectroscopy and XRFs that Serena talked about. And so that corresponds to like the excitation of very, very tightly bound electrons, like core electrons. And once we get into the visible region of the spectrum, it's 1 to 4 electron volts. And 1 to 4 electron volts, that is about the energy of a chemical bond. And that is important because that means if you apply radiation in that region of the spectrum, you excite valence electrons. And the valence electrons is what make the chemical bond. So that means with optical spectroscopy, you are directly looking into the chemical bond. That's why optical spectroscopy is really the central spectroscopy for chemistry, because it happens at energy scales that are the same as chemical phenomena, like making and breaking a bond. And the reason, that's why there is the entire field of photochemistry, where you can use light to make and break bonds, do catalysis and all kinds of fancy things. So that also means if you're really interested in chemistry and chemical bonding, like optical spectroscopy is like your first target, because it is the spectroscopy that talks to you about the actual electronic structure, the actual chemical bond. All of the other spectroscopies here, they talk about the consequences of chemical bonding, but not the chemical bond itself. Right? So if you go down in energy, you don't have enough energy in the photon anymore, like to do anything tangible to the molecule. If you use infrared radiation, you just get the molecule to vibrate, and that's it. Yeah, and so that the techniques would be IR and Raman spectroscopy. And if you go further down to microwaves, you cannot even like induce a molecular vibration, then you can just flip spins. And if you go further down to radio waves, then you can just flip nuclear spins. So these are energies that are tiny, 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 tiny with respect to like the energy that is in a chemical bond. Again, chemistry is right here, and that's what makes the appeal of optical spectroscopy, and I hope to convince you that MCD is one of the particularly powerful techniques in optical spectroscopy. Now, what you probe then in optical spectroscopy are actual states of the system. And I will harp on that. I think I'm probably infamous for doing this, but I feel that there is like infinite confusion also in textbooks, where people really don't understand the difference between orbitals and states. And like please open your heads now. That is centrally important. If you understand that, you really understand a lot more about spectroscopy than most people and most textbooks do. So let's assume you have an arbitrary compound, and as we all know, it is not mandatory, but as we all know, there are orbitals associated with that compound. Now, in order to define one electronic state, so first of all, you need to fill in electrons into these orbitals. And there is a certain occupation pattern associated with a given state, and that is the electronic configuration. It simply tells you like how many electrons are sitting in which orbital, and they can be either 0, 1, or 2. Okay, but that's not enough. So that simply tells you which orbitals are occupied and which are not. And then the second thing that you need is to count the open shell electrons and figure out what the total spin of that state is. And in this case, it's very easy. There are 2 electrons unpaired, and they have parallel spins, so that must be a triplet state. And as you know, and like I think your EPR lectures have like harped on that, there is a second quantum number associated with the spin with its projection on the z-axis. So when I draw this diagram here, I really mean 3 states, right? Because M can take the values S, S minus 1, S all the way up to minus S, which for a triplet is 3 values, MS equals 1, 0, and minus 1. Yeah, and that correspond to different orientation of the spin magnetic moments of these unpaired electrons. All of the other electrons that sit in doubly occupied orbitals play absolutely no role for the total spin, right? They have their magnetic moments paired and they're magnetically blind, yeah? So it's the unpaired electrons that count. There are many, much more complicated situations where the total spin cannot be determined that easily from a molecular orbital diagram, but that is a subject that probably would take me an entire lecture to explain to you. Now the third thing that there is symmetry. Now if the molecular framework has symmetry higher than C1, and I know you all heard group theory at some point, then there is also a symmetry associated with the electronic state, meaning the entire state transforms according to the irreducible representations of the point group, as do each of the orbitals. And in order to figure that out, what you need to do is to take the direct product of the irreducible representations of just the singly occupied molecular orbitals. That is important, right? So everything that's closed shell is simply totally symmetric, and that means the symmetry of the state is determined by only the unpaired electrons. Okay, and these are the three things that you have to figure out in order to determine the electronic one electronic state. You can summarize it in a symbol like this, where you have the occupation vector here, and then you have the total spin, its projection on the z-axis, and you have the symmetry quantum number. And then you call that, if you want to look fancy quantum mechanically, then you write a psi here, and you write psi sm gamma to give you that same information. And that is only the I state. It could be the ground state here. Here it's certainly the ground state, but it could be any excited state as well. And so we call this the wave function for this state. And in this world, you can only observe states. You can never observe orbitals, right? These things here you can never observe. They're not physical observable. So if you read papers where people have observed this orbital or that orbital, that's all wrong. Then is right. Then is okay. You cannot do this. Everything that's observable in this world is related to the many particle states of the system. That is the simplest way you can visualize that. In reality, states are much more complex than the human mind can decipher. Okay. Now that was a ground state. Now in transition metal complexes, you have all kinds of fancy electronic states. And if you look at it, so there are orbitals that are mostly associated with the metal, so the metal d orbitals, and I know Serena has talked to you about that at length. Then there are orbitals, say, of the first ligand and the second ligand, and then there are unoccupied orbitals of the first ligand and the second ligand, and so on. Now, if you have excitations, transitions of electrons between those orbitals, you go from one state to another state. If you say promote an electron within the metal d shell, then we call this a dd excitation. If you promote an electron from a filled ligand orbital into an empty metal d orbital, we call that a ligand to metal charge transfer, or LMCT excitation. If we promote an electron from a predominantly metal-based orbital into an empty ligand orbital, then you call that a metal to ligand charge transfer excitation, MLCT. If you promote an electron within the same ligand, so from ligand 1 to an empty orbital of ligand 1, then we call that an intraligand excitation. And if we promote an electron from a filled orbital of ligand 1 to an empty orbital of ligand 2, or vice versa, we call that a ligand to ligand charge transfer excitation, or LLCT. Now, basically all transition metal compounds in dn configurations other than d0 and d10 have dd excitations. Now in the visible region, LMCT excitations you basically see for more oxidized metals, where the metal d shell lies relatively deep in energy. So quite typically, say if you look at iron, you would see LMCT excitations for iron 3, but rarely for iron 2, and certainly not for iron 1 or iron 0. Yeah? MLCT excitations you have for low valent metals, where the metal D shell is relatively high in energy, so that it takes less energy to promote an electron from here to here than from here to there. Yeah, so quite typically for iron 2, for example, you would have MLCT excitations if the ligand offers low-lying empty orbitals. Intraligand excitations are very prominent if you have like extended pi networks in your ligand, and the most prominent is certainly porphyrin. And like the porphyrin ring, like everything you see basically in the spectrum of porphyrin are intraligand excitations. And ligand-to-ligand excitations are more common than we think they are, and they're particularly prominent if you have metal-ligand radical assemblies. Then you very often observe very fancy ligand-to-ligand charge transfer excitations. So these are the type of transitions that you have to worry about. Now, there is very little that you can say in general about these 4 types of excitations, but of course there is ligand field theory to talk to you about the states that can form for excitations within the D shell, and I know Serena went through that with you in detail. And for just that class of excitations, the Tanabe-Sugano diagram tells you exactly what electronic states arise, what their symmetries are, and what their total spins are. For example, here for the D2 system, your ground state in an octahedral ligand field is triplet T1. And now you would observe in a spectrum spin-allowed excitations, and these are to triplet T2, triplet T1, and then a very high-lying triplet A2. And if you look at actual spectra, like vanadium hexaqvo 3+, you would find exactly these D2D excitations that ligand field theory is predicting. So far, so good. You can also visualize these different types of excitations by electron difference density plots. So what we're plotting here now is the difference in electron density between the excited state and the ground state, where negative, yellow is negative, is electron depletion, and red is positive, is electron gain. So what you see here is that, like in a typical D2D excitation, there is a bit of like charge movement, but it's confined to the metal center, and at the entire ligand framework, the electron density is not changing. So that is a very local transition. For ligand to metal charge transfer transition, now here you have a ligand that is, I think in this calculation, a chlorine ligand, and that promotes an electron to the metal. You see that like the electron density around the chlorine is depleted, and around the metal you gain electron density. For an MLCT transition, it is quite different. Here you see like electron depletion at the metal, and here you can like make out like electron gain in the pi star orbital of that ligand. So that is all good. And here's a pi to pi star transition of like a porphyrin ring, where you see nothing is happening in terms of the electron density at the metal, and all electron movement is happening in the porphyrin ring. So that is a nice way of displaying like what is physically happening in these electronic excitations. Now, there is electronic excitation, and that not all electronic excitations are created equal, and there is a selection rule. So if we like visualize that, so we have here like the sequence of many particle states. So these are not orbitals. So anyone like who pops in like orbital when I draw these vertical bars, that's not what it is. That's wrong. These are the many particle states of the system. Here's the ground state. Here are the various excited states. And now when a photon of the right energy hits the molecule, it may be promoted to that excited state, or it may not. And the probability for that event to happen, that is called the transition probability, and it's associated with the very famous Fermi's golden rule that tells you that the probability for the system to proceed from the initial state and the final state is the matrix element of the perturbation squared. Now, what is the perturbation? The perturbation is then the Hamiltonian that is associated with the light wave, and we know what that is. That is the electric field and the magnetic field of the light wave acting on the molecule. And of course, the electric field and the magnetic field of the light wave are doing very different things. So that probability for the transition might be very high. Then you get an intense peak in the spectrum, or very low. Then you get a less intense peak in the spectrum, or it might be zero, and then you see nothing. Okay? And there are essentially 3 types of transitions that you can make in molecules. Only 3 types. Yeah? So there is an electric dipole transition where the electrons of the molecule are interacting with the electric field of the light wave, and then you get an electric dipole transition. And that is the most common type of transition in optical spectra. I would say like 99.99999% of all transitions you see in an optical spectrum are electric dipole allowed transitions. Now there are electric quadrupole transitions, so that is a higher multiple moment of the system, and you only see that the energy dependence of that is like energy of the final state minus energy of the initial state third power, right? Whereas for electric dipole transition is first power. So these transitions only become important if like the frequency of the light is very high, the wavelength is very short, and then the energy of the light wave is very high. So basically electric quadrupole transitions occur in X-ray absorption spectroscopy at high energies, and even there they're not very prominent. They basically only see them if the electric dipole intensity is vanishing. And the third type of transition is a magnetic dipole transition. That is a totally different type of transition. For an electric dipole transition, the light wave want to grab an electron and move it from one place to the other. And for a magnetic dipole transition, that is different. The light wave, the magnetic field of the light wave will want to take an electron and like spiral it into a different state. And so for a magnetic dipole transition, you see them in EPR spectroscopy. And they're also important for circular dichroism spectroscopy, but like funny enough, they're not important for magnetic circular dichroism spectroscopy. Yeah? So when we talk about EPR spectroscopy, we talk about magnetic dipole transitions. Now there are spectroscopic selection rules associated with this, and Serena told me that she showed you that slide and you had a definitive reaction to it, and so I thought that I show it again to you. That is, because I think as I figured you liked it that much that you certainly wanted to see it again. Okay. Let's reiterate. The information about the allowedness of a transition is contained in that transition dipole matrix element, and you can use group theory to figure out whether that matrix element is 0 or not. You cannot figure out from group theory whether it's large or not. You can only figure out whether it's 0 or not. So and the first and important selection rule here is a spin selection rule, which tells you that the initial and final states must have the same total spin. That is a strong selection rule up to at least the end of the first transition row. And that means that like spin forbidden transitions, say, come with molecular extinction coefficients of, say, 0.01 or lower, but a spin allowed transition can have extinction coefficients of 100, thousands, and 10,000s even. Yeah? Now, in the second, and that is a weaker selection rule, is a spatial selection rule. And like if you reconsider your group theory, then you say that the direct product of the initial state, the final state, and the perturbing operator must contain the totally symmetric irreducible representation. And now only for your orientation, the electric, if you look at your group theoretical tables, the electric dipole transforms as x, y, z, the magnetic dipole transforms as rx, ry, rz, and the electric quadrupole transforms like as these products of coordinates. Now, most importantly, if there is a center of inversion in the molecule, for the electric dipole you have a selection rule that tells you that only gerade to ungerade or ungerade to gerade transitions are allowed. That is why DD transitions and d orbitals are gerade, that DD transitions in transition metal complexes are forbidden, and that is so-called Laporte selection rule, and hence D to D excitations are weak in the optical spectrum and Laporte forbidden. Good. Now we come finally to MCD spectroscopy, that we have reiterated that, and we ask ourselves, MCD spectroscopy, how and why? And if you ask yourself, why should I care, then watch it, then it's right. So now I've set you up like that you should care. And I hope at the end of the day, then like you are convinced that it was worth it. Okay, let's look at the MCD experiment. So it's spectroscopy. You have a light source. You have a light bulb, basically. That's it. And the light that is created passes through a monochromator, so you get monochromatic light. Light of one fixed wavelength or frequency. Now, in addition, the only thing that turns an absorption spectrometer into a CD spectrometer is that you have a photoacoustic modulator, and that modulator creates alternatingly right circular polarized light and left circular polarized light. It operates at a certain frequency. So say with 100 hertz or something, you have RCP and LCP light. That light eventually is detected at a detector that is tuned to the same frequency. Yeah, so the detector simply sees there is a photon coming, but since it's synchronized with the modulator, it knows whether it is an RCP photon or an LCP photon. Yeah, so that is a standard photomultiplier tube here that is sitting in the detector. And in the middle there sits something very bulky, at least for the fancy MCD spectrometers. For example, you can do the MCD experiment in a perfectly regular CD spectrometer and put a permanent magnet around the sample compartment. There are commercial vendors who sell you for ridiculous money like a magnet that you can put into the sample compartment. Then you have one magnetic field and you can carry out an MCD experiment. That's perfectly valid MCD spectroscopy. It doesn't use the full potential of the method, but it's perfectly valid. Now, the powerful MCD spectrometer have a fancy liquid helium-cooled magnet, superconducting magnet here, and that magnet creates a magnetic field in the propagation direction of the light. So in this direction here, it creates a field of variable strength, and the good commercial magnets, they reach magnetic fields between 0 and 11 Tesla, roughly speaking. Yeah. That means that the electric and magnetic field components are perpendicular to the propagation direction of the light, and that means also perpendicular to the direction of the magnetic field lines. Okay, so that is it. And the MCD signal is simply the following. It's the absorption of left circular polarized light minus the absorption of right circular polarized light minus the same at zero field. Yeah, so it is only the field induced circular dichroism. Yeah, so the circular dichroism spectrum is the baseline of the MCD experiment. Yeah, so that is the natural circular dichroism, and that is the baseline. Now, all of you know, in order to have a natural circular dichroism, you need a chiral substance. MCD does not require a chiral substance. It exists in all matter, and the reason is due to the presence of the magnetic field, you break all chirality that might be inherent in the molecule, and that is why you have an MCD signal in absolutely every molecule on this planet, right? Okay, as long as it absorbs, there is an MCD signal. Okay. That is it. Now that experiment has 3 dimensions. I will reiterate that time and again. You have the wavelength of the light, you have the strength of the magnetic field, and you have the temperature. And in a good magnet, you can control this temperature between roughly 1.5 Kelvin and room temperature. So these are 3 important variables to play with, and in all of them is a lot of information, as I'm going to demonstrate to you shortly. So we can already write a very innocent equation that tells us what the strength of the MCD signal would be. Now the strength of the MCD signal would be the concentration of the sample times the thickness of the cuvette times the energy difference between the final state and the initial state. That is just the electric dipole type oscillator strength that I talked about. Then a sum over all possible initial states, J, the Boltzmann population, the fractional population of that state at the given temperature and the given field. And then a sum over the final states, where you have the probability to absorb a left circular polarized photon minus the probability to absorb a right circular polarized photon. Got it? So there's nothing happening, right? So this is the same. So this all is just the absorption probability of left circular polarized photon minus probability of observed right polarized photon. That's it. And that weighted with the probability of meeting the system in one of the initial states, J. Okay. Let's look at that, how it looks in practice. So that is an instrument we built at our lab maybe 10 years ago. Now we have a fancier one that looks exactly the same, but it's much better spectrometer. So basically here you have a commercial CD or modified absorption spectrometer, and then you have like an optical path here, and like here sits a very carefully shielded detector, and that is what makes this experiment such a pain in the neck. And like it looks very simple, but there are many people who try to build an MCD spectrometer and never got it to work. And I strongly recommend to you, if you want to build an MCD spectrometer, don't let a company do it for you. Like hire a physicist who knows what he's doing, and then it will still take that physicist probably at least a half year or a year to make it happen. And the reason for that is that these magnets here, these superconducting magnets, they have really nasty stray fields. And you don't need much of a stray field like to mess with both the modulator here and the detector here. And you can get horrible artifacts in your spectra from like the interference of the stray field from the magnet with either the detector or the modulator. So that needs to be very, very carefully done and very, very carefully shielded. Okay? So you see there's like new metal around here, and like there's all kinds of precautions that we had to take. Now the light, of course, many of the commercial CD spectrometers, like they're built in a way that like all of the light, well, the light comes out here and is already detected here, like within like 5 or 10 centimeters, and that's why they have a beam that goes like this, right? But here our detector is like 2.5, 3 meters away, and if your beam goes like this, then of course like no photon will ever hit the detector because you have lit up the room. And that wasn't the purpose of the experiment necessarily. So you need to focus that beam, and that comes with its own set of issues because like lenses mess with the polarization of the light. So you have to be careful that your beam doesn't depolarize before it hits the detector. So if you do it carefully and you have a nice spectrometer, then it gives out a focused beam, and that focused beam is then focused by lens onto the sample. The sample actually sits in a cell like this, so that is like a copper cell, and it needs to be made out of a conducting material, so that like heat conducting material, so that like the temperature at the sample is really the temperature that you also have like inside your cryomagnet, and it sits on top of a rod that is like being pulled down into the sample compartment here, and this is how it looks. Now, importantly, that sample needs to be transparent even at cryogenic temperatures. And you know what happens if you just take an aqueous sample and you freeze it. It becomes icy, and as it becomes icy, it becomes opaque, and as it becomes opaque, it will not let any light through. Right? Then your MCD signal is like 0, or infinity is simply undefined. So in order to make sure that you can pass light through, like if you insist on like a solution, you have to add a glassing agent. And that glassing agent might well be 50% glycerol. And working with 50% glycerol is not fun. It's like very viscous stuff that is not very pleasant to work with. Your protein might not like this treatment, so you have to carefully check. But you have to have a transparent sample. Very often it also happens that you have a sample, you put the glycerol in, everything looks fine, you dump it into liquid nitrogen, it gives a nice glass, you put it into the spectrometer, and all of a sudden, crack, the glass collapses and it gets opaque and your signal is screwed. And so you need to monitor that carefully. If you have a solid sample, say for model complexes, you can also make a mull. The mull will scatter the light, which is not helpful in terms of detecting your MCD signal, but if you do it carefully enough, you can still do it. So there are certain challenges, experimental challenges, but with a little bit of experience, they can be controlled. Good. So now why MCD spectroscopy? So first of all, it's a sensitive technique, especially you can go into the near-IR region of the spectrum, and that is very hard to do with absorption spectroscopy, especially in the in aqueous samples. You have relatively high resolution because it's a signed quantity. The MCD signal can be positive or negative. It's site selective. You can study, like in a sample that has multiple metal sites, you can have a fair chance of being able to study these sites selectively and separately. It's a multidimensional technique with magnetic field, temperature, and wavelength. It does not require isotopic enrichment, as, say, Raman spectroscopy does, or Mössbauer spectroscopy often does, and it's certainly not restricted to certain elements, right? And so it's not an element-sensitive technique like X-ray absorption spectroscopy. Unlike EPR, MCD has no problems with integer spin states. It is not even restricted to paramagnetic species like EPR is. And then there is, I think, an aspect that can't be overemphasized. It studies the ground and the electronically excited states at the same time. I will explain to you what I mean with that. And certainly it puts severe constraints on possible assignments. So if you're interested in going deeper into the electronic structure analysis, then MCD is definitively a very strong friend of yours. You don't have to do this if you go out of this lecture and say, oh God, I don't want to have anything to do with that electronic structure crap, then you still have all of the rest that like you can really use to your advantage. But like if you're curious and if you're adventurous and you happen to like theory, which I don't know how many of you do, but but then this is a very powerful friend. So now now I want to reiterate these points a bit and illustrate them with examples. Now, these are the dimensions of an MCD experiment. So first of all, there is the spectral dimension. You have like the spectrum as a function of like wavelength or wave number. Actually, let me make a little remark here. I know that like 100.0% of all biochemists plot their spectra as a function of wavelengths. I know that's how you grew up, how you're used to, but it's not the best way to plot an optical spectrum. And the reason for that is that the wavelength is inversely proportional to energy. Now, the phenomena that you observe, namely transitions between different states of the system, that happens on an energy axis. So if you pass on from wavelength to wave number, so which is 10 to the 7 divided by lambda, then you have a scale that is linear in energy, and that is a much fairer display of what is actually happening in your molecule. You will have noticed when you plot your spectra on a wavelength scale that like in the red region, so the low energy part, your bands look broad, and if you go towards the UV, your bands look sharp. That is simply an artifact of like displaying like these spectra on the wrong scale. Now, if you plot them on like an energy scale, your bands practically always have the same width as they should, and this is a fair way to look at an optical spectrum. So that's a discretion. And so you see that these spectra look kind of funny, right? They look kind of complicated. They have like positive peaks and negative peaks, and there's not a lot of wiggling going on. Now you can go anywhere like on this spectrum, like here or here or here or here or there or wherever, and then keep the wavelengths fixed and vary the field and the temperature. And the way you plot that is you plot on the x-axis a reduced variable, beta b over 2 kt. So where beta is a Bohr magneton and that's a Boltzmann constant. So basically on a b divided by t axis, and I tell you later why that is. And then as you basically, the way it's done is you keep the temperature fixed and you ramp up the field. Yeah? And that gives you a so-called magnetization curve. And for a spin 1/2 system, this is how that magnetization curve looks. So first, like the increase of the signal is linear, and then eventually it saturates off. And it saturates off as a hyperbolic tangent, and that hyperbolic tangent that has in it only like your experimental conditions, B and T, natural constants, and then one thing that depends on the molecule, and that is the G value that you also measure in EPR. So here's a connection between the actual excited state that you reach here, like these are actually electronically excited states at like tens of thousands of wave numbers, and the EPRG value that you normally measure in an EPR experiment at, say, like 0.3 wave numbers at X band. Yeah? So you have an optical measurement of an EPR quantity. So the EPRG value is a ground state property. It only depends on the properties of the electronic ground state, yet you can measure it by doing an excited state measurement. Now, traditionally, the MCD signal is expressed in terms of like 3 contributions. And I will explain to you what these contributions are a bit later. And they're called A, B, and C terms. In that traditional way, then the signal is always linearly proportional to the magnetic field. So the traditional way to look at it carries only up to here. And then starting from here, the theory is wrong because the signal is saturating and no longer linearly increasing. And I will explain to you these 3 contributions, A term, B term, and C term. They correspond to different mechanisms that give rise to the MCD signal. My pointer is dying out here. If somebody has a pointer with a functioning battery, that would be appreciated. And so here you see that multidimensional nature of the MCD experiment. That is like a compound. Thank you. So now watch me getting confused with 2 of these things. And hey, I'm a theoretician. This thing has 3 knobs. Then is that 2 too many? Then okay, here we go. Okay, so here is that model compound that, like, I think I come back to a couple of times in the lecture. It's iron EDTA peroxide. So you see it has a very rich MCD spectrum here in the visible, like ultraviolet region, visible region, near-infrared region. And here's something funny happening. So that is a spin 5 half system. And now if I put like the wavelengths to either here or here, I get like really funny magnetization curves that go up and go down again. And like for different temperatures, they don't overlay. And everything is pretty funny. Whereas here, if I take the data here, then I get these like so-called unnested curves where everything overlays for each temperature. So are you confused? That's good, because that hasn't been understood for a very long time, and it calls for an explanation. But just for the moment, take it as part of your curiosity. You have something observed, and what you have observed is that the magnetization behavior of the MCD depends very strongly on the wavelengths at which you take the data. So there is lots and lots and lots of information in that data. You only need to understand how to make it usable, and I will tell you that. Now, even if you look superficially at the MCD spectrum, then you will see, like, for an absorption spectrum like this one, it's basically a relatively unfeatureless blob. But if you look at the MCD, and in particular if you combine it with the natural CD spectrum, you see that there is a lot of structure. And you could never have like fitted like 12 or 13 electronic transitions or bands here under this absorption spectrum without getting punished by your advisor. But like given with the MCD, then is you can resolve all these electronic transitions, right? So you make out of a featureless blob of like trailing absorption, you can make a highly resolved optical spectrum that you can subject to detailed analysis. And that is like invaluable. If you look at MCD together with other spectroscopic techniques, and I strongly advise CD, EPR, and resonance Raman, you have an extremely powerful set of tools available to analyze the electronic structure of your molecule. Now here's an example for the site selectivity of magnetic circular dichroism. If you look at an enzyme like cytochrome C oxidase, it has several metal sites. And so, as you all know, it has a heme center, then a coupled heme copper center, and it has an electron transfer copper A center. And now most of the absorption spectrum is dominated, obviously, by the absorptions of the porphyrin. But there are also absorptions of the copper A center, especially here, like in the near-infrared region, where like the heme doesn't absorb. And so essentially, if you use MCD, you can set your MCD spectrometer to this wavelength here, and you get the magnetic properties of the copper A side, and you can set like your MCD spectrometer to here, and then you get like the magnetization, the magnetic properties of the heme site. Now, if you take, say, a squid experiment, like a magnetic susceptibility measurement, you only get like the sum of the magnetic properties of these two metal centers. But you can really study now these metal centers separately. And that's great. You can do chemistry to them and can watch like what these metal centers do individually. So you have a site selectivity that you do not have in most other measurements. Yeah. Okay, so that's great. Now, MCD is a powerful fingerprint. So even if like nobody really understands like every single detail of these complicated spectra, they are very characteristic. For example, now I've taken the example of hemoproteins for the oxidation and the spin state of the metal. So for example, here's low spin iron 3 porphyrin, high spin iron 3 porphyrin, low spin iron 2 porphyrin, high spin iron 2 porphyrin. They're all totally different, right? And so basically, taking one MCD spectrum, in case of doubt, will tell you without a shadow of doubt what the oxidation and spin state of the metal is. For example, low spin iron 2 is essentially MCD silent, has super weak MCD signals. I'm sorry for like the small letters, you can probably not read it. High spin iron 3 has a very rich MCD spectrum, however with very low intensity. Low spin iron 3 has very intense, richly featured MCD spectra. Especially there is a funny MCD here in the near-infrared region of the spectrum. And high spin iron 2 also has characteristic MCD. Now, Andy Thompson and Miles Cheeseman over the years, they have analyzed this part of like the low spin iron 3 porphyrins very carefully. And they have done that as a function of the axial ligand of the low spin iron 3 porphyrin. And so these are actually ligand to metal charge transfer transitions of very low energy. And so what you can see, you can correlate the shape and the position of these bands with the nature of the axial ligand. Again, sorry for the weak print. But basically from these spectra, you can readily figure out whether there is an imidazole, whether there is a thiolate, whether there is an amine or deprotonated carboxylate or whatever the axial ligand is. Here is the fingerprint in the MCD spectrum. Again, there is no theory involved whatsoever. You see no equation. This is simply like a catalog of spectra that you can correlate with what you have in your own system. So it's a great way of determining axial ligands, for example, in low spin ferric centers. Now here is integer spin systems, and for integer spin systems you know that they are pain for EPR, and the reason for that is zero field splitting. Now if you have, say, a triplet state, S equals 1, and your zero field splitting is positive, then your lowest energy state is ms equals 0, and your excited states are ms plus minus 1. Now if that zero field splitting here, d of the ground state, is larger than the energy of the photon in your EPR experiment, then your EPR is like too anemic to induce any transition from here to here, and very often you don't observe an EPR signal at all. However, the MCD doesn't even try to make this transition. The MCD makes a transition to an excited state that is like orders and orders of magnitude higher in energy. And so what you observe here are the transitions from the ms equals 0 component of the electronic ground state to the ms plus minus 1 components of the electronically excited state, and that is always possible. So whether you have an integer spin system or a half integer spin system does not matter to MCD at all. Okay, so that is great. Now, if you try to conduct an absorption experiment in the near-infrared region of the spectrum, I don't know how many of you have done that. When I was a PhD student, I had a great, nice little old Carey spectrometer, and I took my sample. I was all excited, and I thought, okay, let's measure all the way up to 2,000 nanometer, and it happened. And I was scanning and scanning and scanning, and then came 1,200, and then the spectrometer made bang and made funny noises. And the reason for that, of course, is that in that region of the spectrum, you have overtones of water vibrations, right? And so there is quite a lot of water in aqueous solution. It's like 55 molar water, and even if these absorptions are not very strong, they completely clutter your absorption spectrum, and you don't have a chance really in absorption to figure out whatever absorption band there might be. However, these low energy electronic transitions, they're really, really important because they contain absolutely critical electronic structure clues. Now, what you can do now in the MCD spectrometer is to deuterate your buffer. And so if you do it in D2O, then these overtones are higher in energy, so you see they're not here anymore. Then the absorption spectrum is still a pain in the neck because of like residual H2O that you can probably not exclude. But the MCD spectrum you can readily take. And that is nice because that offers you that entire range from like 10,000 wave numbers to about 5,000 or 4,000 wave numbers, and you can figure out many of the important electronic transitions. And I want to like only give you a glimpse with like one example. And that is quite nice work that Ed Solomon has done with his co-workers over the years. And that is that he's figured out like what the relationship is between these near-infrared transitions and the coordination geometry in high-spin iron 2 complexes. And that is an important thing, right? Because high-spin iron 2 exists with an S=2 ground state, so most of the time you have no EPR, or you have no EPR that you want to show anyone. And they're colorless, right? So they have not any transition in the visible region. Maybe they have MLCT transitions, but there are no like DD transitions in the optical region. And so there is, obviously you have Mössbauer, which is a great source, but no offense, Carsten, Mössbauer is not all of the world. It's an important part of the world, but it doesn't tell you everything. For example, you have a hard time figuring out coordination geometry from it, but the MCD is readily amenable to do that. So, now here's a correlation that they figured out, and it makes absolute perfect sense if you paid attention to your ligand field lecture. So for an octahedral site, you have two bands centered around 10,000 wave numbers, split by about 2,000 wave numbers, and that's about the same for all like typical ligand sets that you have in biology. Yeah, and so that is a quintet T2G to quintet EG transition here. That is split by Jahn-Teller or low symmetry effect, and so that is the signature of a 6-coordinate site. Now you remove one of the axial ligands here, and you go to a tetragonal pyramid, and what happens is that like one of those bands moves down to about 5,000 wave numbers. Again, ligand field theory tells you exactly why. For a trigonal bipyramid, you typically have like one transition at about 7,000 wave numbers, and one below 5,000 wave numbers. For a tetrahedral site, you have two transitions at about 5,000 wave numbers. These are stable spectral structural correlations. Now here is one out of like, well, at least like felt 10 to the 8th examples that have been done in this way. And that is the enzyme Rieske. It's one of the many Rieske dioxygenases. And like the Rieske dioxygenases, they have two metal sites, as like the name says. They have a Rieske center that serves an electron transfer, and they have a non-heme active site that are formed by like the famous facial triad, like two imidazoles and a carboxylate. And so what these enzymes do is that they hydroxylate aromatic rings in the presence of O2. So you have like, here's the substrate, and like after the enzyme worked on it, you have two more hydroxy groups on that ring. And like MCD can be used to study that mechanism. So here's the experiment. Now you take the spectra of the enzyme minus substrate, with and without substrate. So here is the holo enzyme, and it has some MCD spectrum, and here is the spectrum with substrate, and it also has some MCD spectrum. Now that will have contributions from both the Rieske center and the active site. So in order to separate them, you need to do a bit of biochemistry, and you can take the non-heme iron center out by treating it with EDTA or cyanide or something, and then do dialysis. And then you only have the MCD spectrum of the Rieske center here, And it looks funny, and it doesn't interest us, right? So that is really not what we are after. We are after the spectrum of the active site iron, and we obtain it by carefully subtracting like this spectrum from this spectrum. Now, and here's a different spectrum, and what it tells you is that in the absence of substrate, you have two bands centered around 10,000 split by about 2,000 wave numbers, and that tells you that in the resting state, in the absence of substrate, that iron's 2-side must be 6-coordinate. Okay? Are you with me? Yeah? So based on these spectral correlations I've showed you, so that's a 6-coordinate iron side. Now, if you do the same trick in the presence of substrate, but the absence of dioxygen, right? So what you see is that there is another band growing in at about 5,000 wave numbers. So what has happened here? So you have added substrate, and the coordination site has opened up, and then the active site iron is 5-coordinate, and it's a tetragonal pyramid. So here you have like watched the enzyme in action. So now put that into a picture of the mechanism. So you have the resting state is 6-coordinate, and you want it to be 6-coordinate to protect the active site from doing Fenton chemistry, right? In the absence of substrate, you don't want this enzyme to react with dioxygen. Now you add the substrate, and what's happening is that the one coordination site is opening up. So the enzyme makes like a subtle conformational change or something, and like one of the axial ligands, in this case water, is expelled. Now you have like a nice arrangement where you have the substrate in the vicinity of a 5-coordinate iron center, and that 5-coordinate iron center is now ready to bind O2. Yeah? So you get the O2 adduct, and what then happens is, of course, not what you have seen in the MCD experiment, but you have just watched these two initial steps. But what's happening is that at the active site, a hot species forms, like a high valent iron center, that attacks the substrate and finally turns over. All of this must be subject, say, to kinetic studies, freeze quench, stop flow studies, and so on and so forth. But what the MCD has given you is an experimental picture of these initial reaction steps. And like I think Ed and his co-workers have figured out that like there are huge classes of iron 2 enzymes that all work according to the same mechanism. And I think MCD has been the prime time experimental method to prove these relationships. Good. So these are my motivation slides for why you want to use MCD. And now we get a bit into the scary parts, and like we move more towards the theory of it. And well, okay, listen to this guy. And then if it's too hard, it's probably not worth doing. But at least the next few slides I show you, they're worth doing. I promise. Yeah. So now the MCD signal can be positive or negative, and there are two distinct cases that you can normally distinguish. I don't know if you care about it, but I tell you anyways. So one of these cases is where almost all of the MCD bands are of the same sign. Yeah, and this is a case of a low-spin iron 3 complex that is actually activated bleomycin. It's an important anti-cancer drug. And if that is the case, that always tells you that there is strong spin-orbit coupling in the ground state. These are invariably compounds that have large G values, and low-spin ferric compounds are a prime example of that. And there is a second class of like MCD spectra, where the MCD spectra dominantly consists of opposite signs. In this case, there is dominant spin-orbit coupling in the excited states of the system that gives rise to the MCD intensity. In order to understand that, we would need to go deeper into the theory, which I'm not going to do today, certainly not because eventually I will run out of time here. But now here's something more important. So this is a goodie for those of you who like theory. But now if you want to like distinguish experimentally between, say, a DD transition and a charge transfer transition, you can use the MCD. And you use the MCD by taking the ratio of the absorption to the MCD intensity, and that is the so-called C/D ratio. And that is a very effective means to determine whether you have a DD transition or a charge transfer transition. Yeah. So what you do is the following. The C/D ratio experimentally is given by, this is the area under an MCD band. So for this you need a Gaussian fit to your MCD and your absorption spectrum, and that is the area under the absorption band. And you simply scale it by K2 over beta B, and that gives you the experimental C over D ratio. Now, the following thing happens is that for a DD transition, you have a large C over D ratio, which means you have weak absorption and strong MCD. And for a ligand to metal or metal to ligand charge transfer transition, you have a weak MCD and a strong absorption. Yeah? So if you have a C over D ratio of smaller than 0.01, that is like empirical, you have a CD charge transfer transition, and for larger than 0.01, you have a DD transition. Let me show you that. That is like a small molecule, is one of like the PETs that you typically have. So here you have a spectrum that has, here in the near infrared region, has some weak absorption, and that comes with strong MCD of about, with C over D ratio of 0.02, and you have very strong absorption, like that is a ligand to metal charge transfer, chlorine to copper charge transfer, that comes with a relatively weak MCD of 0.002. Now, in terms of absolute intensities, like the LMCT is still dominating over the DD here, but it's the C over D ratio that tells you what is what. And so if you're interested in the nature of a given transition, then the C over D ratio can certainly be used to do that. Alrighty, so with that we come to the favorite part of like the lecture. We talk about the theory of MCD spectroscopy, and so all stay tuned and like listen what I got to say. Yeah? Okay. Let's go back here to the beginning and get oriented. This slide is an important slide because it puts you into perspective what is happening. So here we have the electronic ground state multiplet. It has a total spin S, and it has 2s plus 1 component, m sub s equals s minus 1 all the way to minus s. If you put on a magnetic field, these magnetic sublevels will split, and you can observe transitions between these magnetic sublevels with EPR spectroscopy. Yeah? So that happens like on the order of, say, 0 to 10 wave numbers. Now you excite an electron, say from here to here. I think there is a vertical bar missing here where I mean an orbital that this electron can reach. It's not sitting in empty space. And it could, but then you would talk about EXAF spectroscopy, right? And nobody likes EXAFs. Yeah. Okay, and that has a total spin S prime, that has 2s prime plus 1 components ranging from S prime all the way to minus S. Now, of course, if you put a magnetic field on, also these components will split, and there would be an excited state EPR that sometimes you can do that has an excited state G value, and here you have a ground state G value. Okay, and now the MCD transitions happens between the magnetic sublevels of the electronic ground state that are Boltzmann populated, pretty much all of them, right, even at low temperature, and the components of the excited state, all of which at room temperature are absolutely unoccupied, because these are things that happen at like 10,000 wave numbers, or like 20,000, 30,000 wave numbers, right? So please notice that, take this to heart. This is like many orders of magnitude larger than these splittings. Yeah, so you have like a huge excitation energy and very tiny little splittings. And MCD is sensitive to both of this, the very large excitation energy and the very tiny splittings, and that's great. Yeah. Okay, you have seen this slide. So I told you that there are these A, B, and C terms that give rise to the MCD signal. Now, the phenomenology is the following. So f of E is a line-shaped function, probably a Gaussian. Now, the B term is directly proportional to that line-shaped function, and so that is an absorption-shaped band. Yeah, so that is simply like an absorption-shaped band that can be positive or negative. Now, the signature of the A term is that it's derivative shaped, right? It has a shape of the derivative of an absorption band, so it has like goes up and down or down and up. That is the signature of an A term. And the signature of a C term is that it's temperature dependent. Yeah? So this magnetic saturation curve is all C term, right? So if you don't want to listen to anything else I have to say, is that like in bioinorganic chemistry, you pretty much always only ever observe C terms. Yeah? So you can forget about these two and like ignore the babble that I do the next 5 minutes. Yeah? But I want to explain to you where these things come from, the A, the B, and the C term. And in order to do that, let's reiterate that photons have energy, momentum, and angular momentum, right? So that is what I said before, like that circular polarized photons carry plus or minus 1 unit of angular momentum. And electrons as well, right? And so when you excite an electron and annihilate a photon, the total angular momentum must be conserved, right? Okay, that is not hard to do. So now let's do something that is so hypothetical that it is of no concern to you, and let's do atomic spectroscopy. So now we have an atom. And let's say we have an atom that has a singlet S ground state and a singlet P excited state. So for example, neon atom would be one of those atoms. If you never cared about the absorption spectrum of neon atom, that makes two of us, but I think it kind of like nicely illustrates the principle of like what's happening in an MCD A term. So you have a singlet S ground state that is absolutely non-degenerate, so there is nothing magnetic in here. And then you have a singlet P excited state, and in a magnetic field, that singlet P will split into singlet P minus 1, singlet P 0, and singlet P 1. Yeah? Okay, and that means your photon absorption and like selection rules is that you can go from the singlet S to the singlet P minus 1 under absorption of an RCP photon and conservation of total angular momentum. And you can go from the ground state to the singlet P1 excited state with an LCP photon. Now the way I've drawn this is you see that these two transitions have different energy, right? Okay, and so that means it's totally drawn out of proportion. So this is tens of thousands of wave numbers, and this is like a wave number or two, yeah? That means in terms of absorption, like the LCP absorption and the RCP absorption is like slightly shifted from each other, and since the MCD like sees the difference of these two, you end up with a derivative shaped MCD signal. So that only happens if you have excited states that are degenerate. In bioinorganic chemistry, that pretty much only happens if you have diamagnetic hemes, right? Diamagnetic hemes have orbitally nearly degenerate states where you observe A terms. Yeah? But that is the signature of and mechanism for the A term. Now the C term, for that let's take it around and let's have singlet P the ground state. Then in the ground state it would split like singlet P1, singlet P minus 1, singlet P0. And in the excited state you would have a singlet S. Yeah? Then again you have like two transitions that have different energies. But what is more important than these two transitions having different energies, now the singlet P minus 1 and the singlet P1 have very different, yeah?
How do you differentiate A terms from two C terms, one of which is positive and one of which is negative?
By its temperature dependence, because the A term is temperature independent. So you measure the MCD as a function of temperature, and if like it's changing with temperature, it's a C term. If it's not changing with temperature, then and it's absorption shaped, it's a B term, and if it's derivative shaped, it's an A term. Okay? Make sense? Okay, so if you do that at low temperature and say like 4 Kelvin or so, then the population of the singlet P minus 1 will be much higher than of the singlet P1. Yeah? And that means that there will be more RCP absorption than LCP absorption. And that's why the C term will give you a negative signal here, right? By subtracting these two absorption bands from each other. So that is the mechanism of the C term, is the unequal Boltzmann population of the magnetic sublevels of the ground state. That only happens, obviously, if you have more than one sublevel of the ground state. That means it will not happen for diamagnetic compounds if they're orbitally non-degenerate, right? So if you have an S equals 0, like a low spin iron 2, you don't have a C term, right? But like for everything paramagnetic, you will have a C term. Now the B term is awkward cubed. There is a easy to grasp expression for it that I'm sure you memorize after the lecture. So basically it comes from magnetic field induced mixing of different excited states. Nobody has ever come up with something that one could draw other than an equation, like something intuitive. And so I will leave you with that equation here. Now, fortunately, that B term is completely unimportant for bioinorganic chemistry. That is what dominates the MCD of, say, organic compounds. So if you're an organic chemist and you use MCD, like all of these aromatic compounds, they have MCD that is completely dominated by B terms. Nobody understands them, but like they use it as a fingerprint. So they have a library of spectra, and they can identify different types of ring structure and topologies based on the B term. Now you can make like a back of the envelope estimate like of what is more important. I will not walk you through this, but if you like go through this and ask yourself which is the most important, and you set like the intensity of the A term to 1, then quite typically a B term will be 10 times weaker, and a C term, even at room temperature, will be 5 times larger. Now at 4 Kelvin, or like cryogenic temperatures, the C term will not be 5 times larger, it will be 5,000 times larger. And that means that as soon as you have a paramagnetic compound, all you ever observe is C term. Yeah? Okay, and now let's go back to our magnetization curve. And like for a spin 1/2 system, that is fairly easy. As I told you, it will be a hyperbolic tangent, and from that hyperbolic tangent you can determine the G value. Now, of course, the G value is anisotropic, and you will have very, very slight differences in these G values, in these magnetization curves, depending on the anisotropy of the G value and the polarization of these transitions. I will not make a meal out of it, because in practice the resolution of your MCD experiment is practically never good enough to determine the anisotropy of the G tensor. Whenever you can, please do an EPR experiment. For S1/2, like the magnetization curve of an MCD spectrum is intensely boring, and it will not give you very much information. But like the fun really starts when you have a spin greater than 1/2. Then, as I showed you before, you can have all kinds of funny things happening in the MCD experiment. So each of these curves is like one curve by varying the magnetic field and keeping the temperature fixed. Yeah, so isotherms. So this is the lowest temperature. That's why we go the largest in beta B over 2 kT, and it goes up and goes down again, and then you take the temperature from 1.5 K to 4 K, and then it goes up and goes down a little bit, but it doesn't reach the same point here. And so this is something that has not been understood for a long, long time. And so at that point, a new theory was needed, and that theory was, oh my God, like I made that in the cradle days of my scientific life, but it still stands unchanged today. And I do not really want to walk you through it in much detail. So basically what you're using in that theory is the selection rules for the electric dipole operator and the selection rules for the spin-orbit coupling operator. Now, the electric dipole operator will only connect M sub s values that are the same in the ground state and the excited state, whereas the spin-orbit coupling will connect all kinds of different excited state M sub s components. Now, you start from this innocent equation that I've given you, like in the beginning, where you simply have the difference of the probability to absorb an LCP and an RCP photon weighted by the difference in Boltzmann population. And so then you insert all of this perturbation theory. You go through very lengthy derivations, and you end up with one master equation. And that one master equation is important because it really tells you something about the nature of an MCD transition. And I have it on the next slide as well, and I will show it to you. So what this master equation of MCD spectroscopy tells you is the following. that the MCD signal is directly proportional to a collection of natural constants gamma that are of no concern to you, and 4 pi that is of even less concern to you, and is inversely proportional to the total spin of the electronic ground state. Yeah? Then you have an integral that leads you over all molecular orientations, right? Because you have like the magnetic field fixed, and you have like a selection of frozen molecules that like go through all possible orientations of the molecular frame with respect to the magnetic field. Yeah, so that is that integration here. And now that sum here, I, is over all magnetic sublevels. So that is basically over all of the magnetic eigenstates. So I think you have heard a lot about the spin Hamiltonian in your EPR lecture. Now you diagonalize the spin Hamiltonian and you get the magnetic eigenstates, which are linear combination of the different m sub s states of the ground state multiplied s. Yeah? And so Ni is the Boltzmann population of the ith magnetic sublevel. And Sxi, Syi, and Szi are the spin expectation values of these magnetic eigenstates. And Lx, Ly, and Lz is simply like the orientation of the magnetic field. So these are the direction cosines that the magnetic field makes in the molecular frame. So all of this is ground state property. Yeah? So like once you know the spin Hamiltonian of the ground state, you know this, you know this, you know this, and the only thing you don't know are these m's. And these m's are effective transition dipole moments. So this is what connects the ground state to the excited state that you're looking at. Now, if all of these would have the same value, what you would have here is essentially like the equation for the magnetic susceptibility. Yeah, so you can think of like the MCD experiment like as a function of field and temperature, of a polarization filtered magnetic optical measurement of the magnetic susceptibility. And that's great because if you try to measure the squid like of a protein, like you get a huge mess. You get a diamagnetic background from hell and you cannot get good data. Or if you have like a model compound and you have the tiniest bit of like impurities, like your squid is screwed. Your MCT will not be. You only need like one isolated absorption band, and then you get the same information you get from the squid, but you get it from an optical measurement, and that is fantastic. Yeah, so basically here is, in these things, there is the ground state information, the spin Hamiltonian. So you get like a value for zero field splitting, for D, for E over D, and that is nice. Now, these transition dipole moments here, they have to do with the polarization of the electronic transition. I will probably not be able to explain that in detail to you because I'm going to finish in the next 5 minutes. But so here is something that you can normally only get from single crystal absorption measurements. But now you get this information by analyzing the MCD on frozen molecules, like randomly oriented molecules in frozen solution. That is really a big step forward. That is an equation that you can very easily use. If you're like used to fitting EPR spectra, you can easily use this equation to fit MCD data. At the time we tested that, so Carsten, can I go 5 more minutes and leave 5 more minutes for questions? Yeah? Okay. So that theory makes a definitive prediction about like the MCD, for example, of high spin hemes that have an S equals 5/2 ground state, and so you will have 3 Kramer's doublets, and the 3 Kramer's doublets will contribute to the MCD spectrum. Now, without introducing any fitting parameter, like Phil Stevens had published these MCD data, and these are the experimental data, and these dotted lines are the predictions of the theory without any adjustment whatsoever. And so you see that is correct. So essentially you can predict like given that master equation and the zero field splitting, the MCD is correctly predicted. So there's every reason to believe that the theory is correct, and it has been used now for like 15 or 20, almost 20 years, and it has served exceptionally well. Then now, essentially, like I want to walk you through like the 3 possible cases that you have. Now, so you have now a state with a very large zero field splitting, say 10 wave numbers, 20 wave numbers. Yeah. then the zero field splitting is dominating over the Zeeman term, over the magnetic field. Now you have these two possible possible situations. If your electronic transition is polarized like orthogonal to the easy axis, yeah, right? So like the easy axis is the one along which the electron spin is quantized. So it's like the dz value. Then you get a very steep, unnested magnetization curve. And if your transition is polarized perpendicular to that, you get a weak and very, very nested MCD. So without doing any theory, like if you have a large zero field splitting, you can differentiate between easy axis polarized transitions and off easy axis polarized transitions. So that is the weak field case, strong zero field splitting. Now if you have the opposite weak zero field splitting, so say you have half a wave number or even less, then the zero field splitting is basically playing no role, and then the MCD magnetization curve is simply a Brillouin function, and that Brillouin function only depends on the total spin S. So if you have then a weak zero field splitting and you have a magnetization curve, you can figure out the total spin of the system that you have there. But here's a big warning. You really need to know that you have a zero field splitting that is small. Because essentially here in red is then the zero field splitting for a system with spin 5/2 and a large negative zero field splitting with an easy axis polarized transitions, and it almost perfectly overlays with a Brillouin function for spin 9/2. So, and I'm only saying that because people have done that a lot. There are like really, well, questionable papers, for example, on nitrogenase, where people come out with a really wrong total spin by simply assuming that the system will behave like a Brillouin function, but that is not necessarily true. You need an independent confirmation that your zero field splitting is small, and then and only then can you fit a Brillouin function to the MCD to determine the total spin of the ground state. So these are the two cases, strong field case, weak field case, and then there is the intermediate field case, and that is difficult. That is where the zero field splitting is on the same order as a magnetic field. So that happens if like zero field splitting is 1 or 2 or perhaps not more than 3 wave numbers. Then you get this like really crazy nested like magnetization curves that can go on and off. I will not explain that to you in detail because I have 12 seconds left. So basically that complicated shape here arises from the competition of the internal field that wants to keep the electron spin on the easy axis of the zero field splitting, and from the magnetic field, from the Zeeman term, that tries to tilt the spin away from that easy axis. And the larger the field, the more the field will dominate over the internal field. And that is essentially what you see here. Now here the internal field is dominating, and starting from here, like the external field is taking over and it's like pressing the spin along the magnetic field direction, and that's why the magnetization curve is going down. This is your best case scenario. In this case, the MCD is most sensitive to the ground state spin Hamiltonian parameters, and you get a nice determination of the spin Hamiltonian parameters. Okay, I think I've exceeded my time. I've wanted to tell you one more thing, but I will not do this. But I simply will wrap up, okay? Okay, so wrapping up, I very much hope that I've shown you that MCD is all of this, and it's a really powerful technique that you can add to the arsenal of bioinorganic chemistry. And I probably don't want to read all of this here again. These are all of the advantages that MCD has, all of the opportunities that it has. And I've recently explained it like to a friend of mine, and I think like if want to leave you with this and happily take your questions.
Thanks, Frank. Before we open up the floor for questions, just a quick announcement. I sent out the email because I forgot it at the beginning. Those of you who are interested in a quick tour of the DSC facility with Dean Wilcox and Julia Facco, the tour is during this coffee break. You'll be back for the second talk. The tour starts essentially in the next few minutes under the bridge. And with this, I would like to open the floor for questions in case there are some more questions for Frank. Yes.
So if you go back to the slide with the general theory for MCD, if
Sure.
you go back to the so if I summed over I and I integrated over both of those with sine theta, d theta, d phi,
Yes.
do I just get a 4 pi and then the 4 pi will drop out there as
No,
on
no,
the next slide?
the 4 pi is in there.
Right. So if
the
I
4 pi is in there. It's all absorbed in there.
right. So if I integrate over that, do I get like a solid angle or something like that? And the
Yes, yes, you do.
And the 4 pi
Yeah,
drops
you
out
do.
like
Yeah,
on the
it's
next
basically
slide.
the same type of integration that you have for a powder EPR spectrum.
Okay. Thank you.
Yeah.
Aveni?
Okay, this is probably a silly question, but for the C terms, where the intensity is arising from the splitting of the ground state,
Yes.
is there a reason you don't also see a small energetic shift for the C terms, like you do for the A terms?
Yes, so basically every C term has a tiny bit of A term component in it. It's just totally drowned out by the fact that like the C term mechanism is a couple of 100 times stronger than the A term mechanism. Then it's completely correct. Yeah, it's also, of course, you have these splittings there, like in the excited state, that also leads you to shifts. But the bandwidth of the band, like that is one assumption I make in deriving that equation. It's like many orders of magnitude larger than the small magnetic splittings in the excited state. Now, if you would have a monster system that has like a 3000 wave number zero field splitting in the excited state, then that theory would be invalid.
No further questions? Well, let's thank Frank again and go to the coffee break.